In this video, we'll discuss Slurm resources, partitions, and scheduling in the NIH Beowulf cluster. In a previous video, we showed that when a job is submitted to a batch system, it is placed in a queue until the resources requested are available. There are actually several queues defined on the Beowulf cluster. In the Slurm batch system, these queues are called partitions. Different partitions differ in the various resource limits defined for them. Some of these limits are listed here. We can define max CPUs per user, max GPUs per user, the default wall time, the wall time being the time we expect the job to run, the maximum wall time, and finally, which users are allowed to submit to various partitions. And partitions named after an institute or lab are usually restricted to members of that IC or lab. On the Beowulf cluster, the way to discover available partitions and their associated limits is by using the batchlim command, and we'll demo that now. Batchlim stands for batch limits. The first two lines of the output from batchlim show two types of job limits. The first is the maximum number of jobs per user. That's both running and queued jobs. And then max array size is the largest number of subjobs either a job array or a swarm can have. Then for each partition, we list the name of the partition, the maximum number of CPUs per user, the default wall time. In other words, if you don't specify a wall time, this is the wall time that will be set. And then the maximum wall time, which is settable. And additionally, there are some other limits that may apply. So going through these, we first have the norm partition. That's the default partition. If you don't specify a partition, the job will wind up in the norm partition. At the moment, the maximum number of CPUs is over 7,000 with a default wall time of 2 hours, maximum wall time of 10 days. Norm is for single node jobs only. If your job needs multiple nodes, you submit to the multi-node partition. This also has maximum CPU per user of over 7,000. Here the default wall time is 8 hours, and again a 10-day maximum wall time. The multi-node partition also has an option called Turbo, which is a quality of service option, which allows larger numbers for the maximum CPU with the restriction of a maximum 8-hour wall time. You don't actually submit to the interactive queue. This is where jobs that are submitted via S-Interactive wind up. Limits here are 64 CPUs per user, default wall time of 8 hours, and a maximum wall time of 36 hours, and the additional restriction of a maximum of 3 simultaneous interactive jobs. The quick partition is for jobs that will not run more than a maximum of 4 hours. Large mem is for jobs that require more than 256 gigabytes of memory. The GPU partition is for jobs that require GPUs. And finally, the unlimited partition is for jobs that require more than the 10-day maximum otherwise. These have a very restricted number of CPUs per user. The remaining partitions will not be discussed here. And here's how you submit jobs to specific partitions. If you don't specify a partition, the job will be sent to the default partition, that is norm. So to specify a partition, you use --partition, option to sbatch, or to swarm, and in these cases we're submitting to the quick partition. In order to use the turbo QoS along with multinode, you specify --QoS. You can actually submit to two partitions. In this case, we're submitting to quick and norm, and the job will run on whichever partition has the requested resources. And CPU limits are cumulative. So in the above case, resources available, one could get over 13,000 CPUs. Another thing you might want to know about a partition is the node configurations available in the partition and the numbers of CPUs currently available. For this, you can use the freen command. Freen stands for free nodes. For each partition, freen lists the different node configurations present in that partition. Each node type is listed on a separate line. For each node type, we list the partition, the number of free nodes, the number of free CPUs, free GPUs if that's appropriate, and then the node configuration, cores, CPUs, GPUs, allocatable memory, allocatable local disk, and then a number of largely informational features, most of which you will never need to use, with one exception. The features starting with an X stands for the Xeon processor type, and there are a couple of times you may need to use this, which we'll discuss a bit later. So taking the norm partition as an example, we can see that there are 4 different node types in the norm partition. Taking one of these as a further example, so this node type is in the norm partition. The star simply means that norm is the default partition. Free nodes shows 0 out of 510. The 0 does not mean that there are no resources available on those nodes. It simply means that there are no completely free nodes. In fact, there are 4,300 free CPUs of that node type. These nodes are configured with 28 cores, 56 CPUs, 248 gigabytes of allocatable memory, 800 gigabytes of allocatable local disk. The constraint option is used to specify a feature. In this case, we're specifying a 2695 processor type. And there's really only 2 reasons to specify a processor feature. First is on tightly coupled multi-node parallel jobs, for instance, molecular dynamics, and that's because the job will run at the slowest speed processor, and you don't want to mix fast and slow processors. Secondly is for benchmarking code. From one benchmark to another, you would want to keep the clock speed of the processor constant. In the last part of this video, we'll talk about how the batch system schedules jobs. Within each partition, scheduling is done by priority. Priority is based primarily on fair share. Fair share is a measure of the amount of CPU and memory used by a user's jobs. It's measured in CPU minutes and increases as a user's jobs complete and decreases with a half-life of 7 days. Slurm uses backfill job scheduling. In the video covering setting wall times for jobs, the importance of setting reasonably accurate wall times was stressed. The next 2 slides will demonstrate why. This diagram represents a small cluster of 10 CPUs along with the timeline. As jobs are submitted, the scheduler tries to fit the job into a schedule based on the number of CPUs and the wall time requested by the user. So job 1 enters the system requesting 8 CPUs with a wall time of 1 hour. And the scheduler can start that job right away as the resources are available. Second job, job 2, 2 CPUs, 2 hours. Again, the scheduler can start it immediately. Job 3 comes into the system needing 2 CPUs and 4 hours. Now this job can't be scheduled to start until hour 1. Job 4, 9 CPUs, 1 hour. Now this job can't be started until the 5th hour because there are insufficient number of CPUs available until then. Job 5, 2 CPUs, 2 hours. Note here the scheduler is able to fit that job at hour 1. This is called backfill scheduling. Job 6, 5 CPUs, 2 hours. Again, this job can be backfilled. Now note, if the user for job 5 and job 6 overestimated the wall time required to say 8 hours, the scheduler would be unable to start those jobs until hour 6. So an accurate wall time here is in the best interest of the system and the user. The Beowulf system administrators use Slurm reservations to reserve compute nodes well ahead of time. We use this feature for scheduled maintenance periods to ensure that all jobs have completed by the time the maintenance window has begun. So here is another timeline. Here's a reservation being set 10 days before a maintenance window. The scheduler will not start jobs that intrude on the reservation window. So here's job 1 being submitted on day 7 with a wall time of 7 days. The scheduler sees that it can finish this job before the reservation window, and it starts the job immediately. Job 2, submitted at the same time as job 1, has a wall time set for 8 hours. The scheduler sees it cannot finish that job before the reservation starts, and therefore it will keep the job queued until the reservation period ends. Likewise, here's a job 3, say being submitted with 12 hours left before the reservation. It had a wall time set of 6 hours. The scheduler sees it can finish it, and it will start the job. Job 4 has set a wall time of 24 hours. The scheduler sees it cannot finish it before the reservation starts and holds the job until the end of the reservation. Once again, setting realistic wall times is very important. This concludes this video.